Atomic traffic switching in Kubernetes requires two identical deployments and a single service directing traffic based on pod labels. The blue deployment runs the current stable version, while the green deployment hosts the new release in an isolated environment. Kubernetes services use label selectors to identify target pods. Changing the selector value instantly reroutes every new incoming request. Before shifting traffic, the green deployment must reach the desired replica count and pass all readiness probe checks successfully. Readiness probes prevent the service from routing traffic to containers that are still initializing or loading application context data. Avoid patching existing pods. Instead, create a completely new deployment object to ensure the environment remains clean and predictable.
Update the service specification by targeting the version label of the green pods. This edit triggers the endpoint controller. Execute the kubectl patch command to update the service selector programmatically. This method is faster and safer than manual editing. The endpoint controller detects the selector change and updates the API server, which then propagates changes to every node. Kube-proxy on each node updates the local IP tables or IPVS rules to reflect the new pod IP addresses within milliseconds. Existing connections to blue pods persist until closed, while all new connections are immediately routed to the green deployment pods. Set a generous termination grace period to allow active requests to complete before Kubernetes SIG term signals shut down the containers. If errors spike after the flip, immediately revert the service selector to the blue label to restore the previous stable state. Keep the blue deployment alive for a cooling period. Once the green environment is verified as stable, delete the old deployment. For complex routing, use an Ingress controller. This allows for weighted traffic shifting rather than a hard binary switch. The Nginx Ingress canary annotation enables sending a specific percentage of traffic to the green deployment for real-world testing.
Route internal testers to the green environment using custom HTTP headers, while the general public remains on the blue environment. Mirror production traffic to the green environment without returning the response to the user. This validates performance under actual load. A service mesh like Istio provides granular control over traffic shifting using virtual services and destination rules instead of standard services. Define subsets in a destination rule to group pods by version. The virtual service then distributes traffic based on defined weights. Observe error rates, latency, and throughput in real time during the transition. Automated rollback triggers depend on these specific metrics.
Argo Rollouts is a custom controller that automates blue-green deployments by managing the entire lifecycle of the pods and services. Use analysis templates to query Prometheus or Datadog. The deployment automatically proceeds only if the success criteria are met. When an analysis fails, Argo Rollouts automatically aborts the promotion and scales down the green pods to save cluster resources. Sticky sessions can cause users to remain on the old blue environment even after the traffic flip has officially completed. Store session data in an external Redis or Memcached instance. This ensures users do not lose their state when switching environments.
Database changes are the most difficult part. The schema must be backward compatible to support both blue and green code simultaneously. Apply the expand contract pattern by first adding new columns, then deploying the code, and finally removing the old columns. Blue-green deployments temporarily double the resource consumption. Ensure your namespace quotas allow for 2 full sets of pods. The cluster autoscaler may need time to provision new nodes for the green deployment. Factor this delay into your deployment pipeline. Avoid relying on DNS for the traffic flip. High time-to-live values on client machines can delay the switch for hours. Internal load balancers often update faster than external cloud providers. Test the convergence time of your specific Ingress controller setup. Kubernetes uses endpoint slices to handle large numbers of pods efficiently. This improves performance during the traffic flip for massive clusters. Observe P99 latency closely during the switch. Brief spikes are common as the internal load balancer rebalances the connection pool. Run smoke tests against the green service cluster IP before updating the public service. This ensures the environment is functional. Network policies must apply to the green labels exactly as they do for blue. Use generic labels for security rules to avoid gaps.
Ensure both versions have access to the necessary secrets. Decouple secret rotation from the blue-green deployment cycle for safety. Version your config maps alongside your deployments. This prevents the green environment from accidentally using outdated configuration parameters. Sidecars for logging or service mesh must be at compatible versions. Update the deployment template to include the latest validated sidecar images. Inject the deployment version into your logs. This allows for clear differentiation of issues between the blue and green environments in Kibana. Kubernetes audit logs capture the exact time the service selector was changed. Use this for root cause analysis during post-mortem reviews.
Verify that zero traffic is reaching the blue pods before scaling them down. Use metrics from the Ingress controller for confirmation. Blue-green deployments are expensive due to doubled capacity. Use spot instances or temporary nodes to mitigate these additional infrastructure costs. The cycle completes when the green environment becomes the new blue. This continuous loop ensures safe, repeatable, and fast production releases. Integrate these patterns into your CI/CD pipelines. Standardizing the blue-green switch reduces human error and accelerates the delivery of value.